6 feet beneath your foundation. Right now, the ground sits at a temperature that has not changed by more than a degree or two in the last 10,000 years. Not during the heat wave that broke records last July. Not during the polar vortex that froze pipes across 3 states last January. Not during any of the summers or winters that came before either of those. The ground at that depth holds steady at the mean annual air temperature of whatever region it sits beneath. And it holds that temperature with a consistency that no mechanical system ever built by human hands has matched or will match. In Chicago, that temperature is 55 degrees Fahrenheit. In Atlanta, it is 62. In Denver, it is 58. In Phoenix, where summer surface temperatures regularly exceed 110 degrees, it is 67 degrees 6 feet down. In Minneapolis, where winter wind chills drop to levels that make exposed skin dangerous within minutes, the ground 6 feet beneath the surface sits at 52 degrees year-round. The surface above swings by 125 degrees or more across the full range of seasonal extremes. The ground 6 feet down barely shifts by a single degree across the same period. This is not a theory or an estimate. It is measured physics documented by Oak Ridge National Laboratory in Tennessee, where researchers have monitored ground temperatures continuously for decades. The data is unambiguous. Below 6 to 10 feet, soil maintains a temperature equal to the annual mean air temperature of the region, plus 1 to 2 degrees. That stability does not degrade over time. It does not require maintenance. It does not consume electricity or fuel. It is simply the thermal behavior of a mass so large that no seasonal fluctuation at the surface has enough energy to penetrate it before the season changes and the surface temperature reverses direction. The reason this matters to anyone who pays a cooling or heating bill is straightforward. If you can move air through that stable underground temperature before that air enters your home, you can precondition it for free. Hot summer air entering a buried pipe at 95 degrees emerges at the other end at temperatures approaching the ground temperature, somewhere between 55 and 67 degrees, depending on your location. Without a compressor, without refrigerant, without any moving part more complex than a small fan drawing 50 to 80 watts of electricity. Cold winter air entering that same pipe at 15 degrees emerges tempered toward the same ground temperature, reducing the load on whatever heating system the home uses by a measurable and significant margin. The system that accomplishes this is called an earth tube, a thermal labyrinth, or a ground-coupled air system, depending on which engineering tradition is describing it. The concept is ancient. The performance data is extensive. The material cost for a residential installation runs between $300 and $400, and it is effectively absent from American residential construction, not because it was tested and found inadequate, but because the industry that profits from mechanical cooling had both the means and the motivation to ensure it never became standard practice. Engineers measure the efficiency of cooling systems using a metric called the coefficient of performance, which expresses how many units of cooling are delivered for each unit of electricity consumed. A standard residential air conditioning unit achieves a coefficient of performance between 2.5 and 3.5. That means for every unit of electricity you pay for, you receive between 2.5 and 3.5 units of cooling in return. The rest is heat dumped into the outdoor air through the condenser. Thermal labyrinth systems, measured across 47 documented installations worldwide, achieve an average coefficient of performance of 28.7. The electricity required is a small fan moving air through buried pipes. The cooling is delivered by the earth itself. 28 versus 3. That gap represents the difference between a system that costs you money every month for the entire life of your home and a system that costs you almost nothing to operate after the initial installation is complete. The people who knew this best were not modern engineers. They were ancient ones. 2,400 years ago, in what is now central Iran, engineers constructed cooling structures called yakhchal, which translates simply to ice pit. These were not primitive holes in the ground. They were precision-engineered facilities whose physics is still documentable with modern instruments. At the city of Yazd, in the Iranian desert, you can walk inside domed chambers rising 60 feet high with walls 6 feet thick at the base. Those walls were made from a material called sarouj, a mixture of sand, clay, lime, goat hair, and egg whites that achieved insulation values exceeding modern fiberglass bats. The Yakchal connected to underground tunnel networks called qanats stretching miles into distant mountains. Air passing through miles of underground passage emerged at 50 to 55 degrees Fahrenheit, regardless of the desert heat at the surface above. Archaeological teams with modern temperature monitoring equipment have documented Yakchal interiors maintaining temperatures between 25 and 30 degrees Fahrenheit through summers exceeding 115 degrees outside. They were storing ice in the desert, reliably and continuously, for an entire civilization, using nothing but buried passages and thermal mass. No electricity, no refrigerant, no compressor, no service contract, no monthly bill. The Romans arrived at the same principle independently. At the Villa of the Mysteries outside Pompeii, archaeologists discovered air passages in the hypocauste system designed not for heating, but for cooling, extending from beneath the floors into the hillside behind the structure and pulling cool underground air through the living spaces. Infrared thermography studies of excavated Roman cooling channels show temperature differentials of 15 degrees Celsius from surface conditions. The Roman engineer Frontinus documented subterranean air passages providing summer comfort in elite homes across the empire. In Korea, the Ondal system, dating back 3,000 years, included underfloor air channels that historical records confirm maintained interior temperatures between 64 and 72 degrees Fahrenheit through both brutal summers and harsh winters. In the American Southwest, indigenous peoples built semi-subterranean pit houses for 8,000 years, utilizing earth contact cooling that archaeological evidence confirms worked exactly as designed. Every civilization that mastered hot climates discovered this principle independently. Persians, Romans, Koreans, indigenous Americans. 5,000 years of converging engineering across every continent on Earth. Then, in less than 1 century, it vanished from Western construction almost entirely. The mechanism of that disappearance is worth understanding precisely because it follows a pattern that anyone who has paid attention to how beneficial technologies get buried will recognize immediately. In 1902, a young engineer named Willis Carrier stood in a Pittsburgh printing plant solving a humidity problem. His invention became the foundation of mechanical cooling. By the 1920s, the Carrier Corporation had launched a marketing campaign positioning air conditioning as the symbol of modernity and progress. Their materials explicitly framed passive cooling techniques as primitive and unsanitary. A 1930 Carrier Engineering Corporation manual dismissed earth contact cooling as suitable only for cellars and food storage. Industry publications celebrated the triumph of machine over nature, as though dependence on electricity represented advancement rather than vulnerability and ongoing financial obligation. By 1927, the first model mechanical codes had emerged with heavy participation from HVAC industry representatives. By 1945, the post-war building boom was standardizing mechanical cooling as the only acceptable approach. Passive alternatives disappeared from architectural education. The American Society of Heating, Refrigerating, and Air Conditioning Engineers codified mechanical cooling as the baseline assumption for all thermal comfort calculations. By 1980, fewer than 3% of American architecture programs taught passive cooling strategies. The technology was not disproven. It was systematically removed from professional memory through the educational pipeline that produces every architect, engineer, contractor, and building inspector working in America today. Contractors have never heard of thermal labyrinths because their licensing exams never mention them. Building inspectors cannot approve what their training never covered. An entire field of proven engineering vanished, not through failure, but through deliberate exclusion from the institutions that define professional knowledge. While American construction moved in that direction, European building science did not follow. At the Passive House Institute in Darmstadt, Germany, researchers have monitored 847 residential earth tube installations since 2005. The performance data is unambiguous. These systems deliver an average cooling capacity of 3.2 kilowatts, while reducing mechanical cooling demand by 89%. Homes maintain interior temperatures between 72 and 75 degrees Fahrenheit without air conditioning, even when outside temperatures reach 95 degrees. The average payback period is 12 years, after which the cooling is essentially free for the remaining life of the system, which is measured in decades. In Austria, the national building standard requires thermal labyrinth analysis for any structure exceeding 1,000 square meters. At a major hospital in Vienna, an earth tube system has provided 450 kilowatts of cooling to critical care units since 1994. 30 years of continuous operation. Maintenance records show cleaning required only every 5 to 7 years. Operating cost runs 2 cents per kilowatt hour, compared to 8 to 12 cents for conventional cooling. In Switzerland, the Minergie certification program has documented performance data from over 200 monitored earth tube installations. A 15-year longitudinal study from ETH Zurich found zero degradation in system performance over the entire monitoring period. Swiss engineers solved the radon concern that American regulators use to block these systems through activated charcoal filtration combined with ultraviolet treatment, reducing radon to background levels at minimal additional cost. Swiss residential installation costs run between 3,500 and 6,000 francs total. The pipe materials alone cost $300 to $400. 3 decades of European performance data. Thousands of successful installations in hospitals, homes, and schools. Zero degradation over 15 years of monitored operation. And the American Building Code still treats this as though it does not exist. The reasons for that are financial before they are technical, and understanding them is inseparable from understanding what it takes to build one of these systems yourself, and what the actual performance looks like in practice across different climates and soil conditions. The physics is simple. Air moving slowly through a buried pipe absorbs the ground temperature surrounding that pipe and arrives at the building already conditioned. The engineering that makes it reliable rather than problematic comes down to 7 variables. Get all 7 right, and the system runs for decades without meaningful maintenance. Get any one wrong, and you create either a performance problem or a moisture problem that undermines everything else. The first variable is depth. 2 meters, roughly 6.5 feet, is the minimum installation depth for a system that delivers meaningful conditioning in most climates. Above that depth, the ground temperature fluctuates with seasonal surface conditions, and the performance benefit shrinks proportionally. Below that depth, you are into the stable thermal mass that holds its temperature year-round. In climates with deep frost penetration, going to 8 feet provides additional margin and measurably better winter tempering performance. The second variable is pipe diameter and length. 200 to 300 millimeters, roughly 8 to 12 inches in diameter, is the standard range for residential installations. Larger diameter means more surface area in contact with the soil and better heat transfer per unit of airflow. Length determines how much conditioning the air receives before it enters the building. 30 to 60 meters of buried pipe is the documented range for effective residential performance. Shorter runs underperform because the air does not spend enough time in contact with the conditioned soil mass. The Passive House Institute data shows that systems under 20 meters of buried length deliver less than half the conditioning capacity of properly sized installations. The third variable is airflow velocity. 2 to 4 meters per second is the optimal range. Faster than 4 meters per second, and the air moves through the pipe before it can fully absorb the ground temperature. Slower than 2 meters per second, and you are not moving enough air volume to meaningfully condition the living space. A small inline fan drawing 50 to 80 watts maintains this velocity range reliably. Running the fan on a variable speed controller tied to an indoor temperature sensor automates the entire operation with no manual intervention required. The fourth variable is drainage slope. Condensation is inevitable. On a humid summer day, air entering the pipe at 95 degrees and 80% relative humidity will drop well below its dew point as it cools toward ground temperature. The moisture that condenses inside the pipe on a single humid day can measure in gallons. That moisture needs a path out of the system. A continuous slope of 2% toward a drainage outlet at the lowest point of the pipe run is not optional. It is the difference between a cooling system and a mold incubator. Install a clean-out access point at the low end of the run and inspect it annually. The fifth variable is intake placement. The intake opening needs to be a minimum of 15 meters from the building, elevated slightly above grade and positioned away from any source of contaminated air. Dryer vents, exhaust fans, compost areas, areas where vehicles idle, and areas where standing water collects after rain are all incompatible with intake placement. A coarse mesh filter at the intake keeps insects and debris out of the pipe. An MV13 rated filter at the building end before air enters the living space handles fine particulates and biological material. The sixth variable is radon. This is the legitimate concern that American regulators have used to block these systems while ignoring the European solution that costs under $100 to implement. An activated charcoal canister installed at the building end of the system reduces radon concentrations by over 95%, according to EPA-confirmed testing protocols. Replace the canister annually. Install a radon detector at the system outlet and test quarterly for the first year until you understand your specific site geology. Most sites show radon levels well within safe ranges after filtration. Sites in known high radon geology require more careful monitoring, but not system abandonment. The seventh variable is soil contact. The pipe needs intimate thermal connection with surrounding earth. No air pockets, no loose fill that settles into voids over time. Bed the entire pipe run in compacted sand before backfilling. Sand transfers heat efficiently, drains moisture away from the pipe surface, and prevents the soil settlement that creates air gaps around the pipe over time. Wrap the pipe in geotextile fabric where fine soil migration is a concern. The complete material cost for a properly built residential earth tube system is $300 to $400 in pipe, fittings, filter housings, and drainage components. Excavation is the primary labor cost, and a rented trencher handles the digging in a single weekend for most residential properties. The Air Conditioning, Heating, and Refrigeration Institute spent $47.3 million on political activities in 2022. That number exists because every earth tube installed is an air conditioning unit that never gets sold, a compressor that never needs replacing, a refrigerant charge that never needs topping off. The $29 billion annual residential cooling market depends on your not knowing that 55-degree ground temperature is sitting 6 feet beneath your foundation right now, waiting to be used. The Persians used it 2,400 years ago. The Germans are using it today. The physics has not changed, and it will not change. The ground will still be 55 degrees under your foundation long after every air conditioning unit currently running in America has been manufactured, sold, serviced, and scrapped twice over. Thank you for watching this video. Click here to watch another video that might interest you.